In this final example, we are asked to calculate the pH of a 0.20 molar solution of Na2HPO4. Once again, when we analyze the salt, we see that Na is going to be separated from HPO4. And our analysis has been that Na comes from NaOH, which is a strong base, and our conclusion is that the Na is no longer going to want to react with the water. However, we need to pause with the HPO4. And the reason that we need to pause is that if we analyze HPO4, we discover that it is amphiprotic. That means that it can act either as an acid or as a base. And so there needs to be further analysis of this amphiprotic ion in order to determine the most likely reaction that will take place with HPO4 2-. So if we look at the two options that the HPO4 can take in terms of reacting with water, they will be HPO4 2- plus water, and it can act as an acid, so it forms PO4 3- plus H3O+. The second option is HPO4 2- reacting with water, giving you H2PO4- plus OH-. So as we take a look at these two equations, both of them are plausible. But which one is most likely going to happen? And so what we're going to need to do is analyze this in terms of its Ka and Kb values. When we look at our chart for the very first equation, HPO4 over here, giving you H plus PO4 3-, we see that there's a Ka value of 2.2 times 10 to the minus 13. So if we take a look up here, the Ka over here is 2.2 times 10 to the minus 13. Now, when we analyze the second one, we have to take a look at our conjugate acid and conjugate base. And when we take a look at the analysis, we have to go up here and take a look at this equation. Now, unfortunately, this equation is only looking at the Ka of the H2PO4 and not the Kb of HPO4 2-. And so what we need to do is do some calculations to convert the 6.2 times 10 to the minus 8 into the Kb value. So if we do this, the Kb is going to be 1.0 times 10 to the minus 14 all over 6.2 times 10 to the minus 8. When we complete this calculation, we see that the Kb value is 1.6 times 10 to the minus 7. So what is the significance here? If we take a look at the Ka, it is much, much smaller than the Kb. What this indicates is that HPO4 has a smaller tendency to form H3O+ and a larger tendency to form the OH-. Hence, we can conclude that the HPO4, the predominant reaction, is going to be reacting with water to form a base. So the next step after our analysis is to take this second equation and generate our equilibrium chart and then go ahead with our calculation. And so at this point in time, all of you should know how to do this, and so I will leave it up to you to complete this particular example. So once again, in the case where you have identified an ion to be amphiprotic, you have to analyze its respective Ka and Kb values. Now, we run into a problem. We know from above that when you have a negative ion, which is an anion reacting with water, what happens is that it will then produce a hydroxide. So that is anionic hydrolysis. But in this case, we also have an anion that is producing acidic solution. So what do we call that? So in order to differentiate these two particular reactions, a new name is developed. And in this case, the new name is called further ionization. And so in this case, when we take a look at the negative ion, if it behaves in the typical way and forms a hydroxide ion, it will be called, or that process is called, anionic hydrolysis. However, in the case when the negative ion goes ahead and reacts with water to form a hydronium ion, then the new name that we use for this particular reaction is called further ionization.